Hello everyone and welcome to Atencephalon Lectures. Atencephalon is a research company that employs expertise in neuroscience and computer science with the intent of using a regular computer program to control the brain of a living animal. Atencephalon has advanced research in this field, and this series of lectures underscore our belief in this possibility. This is the fourth in our series of lectures. A link to the first 3 lectures is provided with this video. In this fourth lecture, we shall be designing more logic circuits with neurons. We began by designing logic circuits with neuron in lecture 3. We shall continue more of such logic circuits in this lecture. Okay, so in the third lecture, we said this is a neuron, and we use these drawings on your left-hand side in our representation of these neurons. We also did an exclusive OR circuit. We implemented an exclusive OR circuit using neurons, and we saw its equivalent using logic gates. So let's consider another circuit with a logic expressed in the truth table below. So this is the truth table, and we are expressing a logic using this truth table below. So first we shall examine what a logic circuit designed with logic will look like when we shall also examine a logic circuit designed with neurons. So we start by designing logic circuit with logic gates, and then we'll now look at how it looks like in neurons. So if we are to design with logic gates, this is what it will look like. This circuit designed with a logic gate will look like this. By the way, this logic gates, where this circuit was designed from employing Kanoff map, K-map. For those people in computer science and people who design logic circuits, they are already aware of K-map. K-map is just a map representation of this table, and then we use that K-map to do a reduction. When we are able to reduce this circuit, we are able to minimize the number of electronic components we use in designing the circuit. So K-map was employed to design this circuit. All right, let's see what this circuit will look like in using a neuron. Now, Odunsi is a proprietary method that is used by Atencephalon in the design of logic circuits with neurons. By the way, Wale Odunsi is one of the staff of Atencephalon, and he came up with this brilliant idea that has helped us in designing logic circuits with neurons. So with this method, we're able to minimize the number of neurons we use in implementing a logic circuit. So it's called Odunsi's method. All right, so using Odunsi's method, this truth table can be designed with this set of neurons. And we're going to go through it so we can see if truly this logic circuit designed with neuron expresses what is represented in this truth table. So let's begin. When we have 0, 0, as shown by this pointing arrow here, when we have 0, 0, A is 0, B is 0, and C is 0, the output is 0. We knew from our from the third lecture that when A, B, and C is not firing, then Z is not going to fire. Nothing is going to happen in this circuit. So clearly, the first logic that we have here is being obeyed. Let's look at a second. Now with this arrow, we have moved to the second rule here, where A is 0, B is 0, and C is 1. That means A is not firing, B is not firing, but C is firing. Let's see how this logic here represents what we have in this truth table. So when A is firing, so we are going to follow the action potential as it leaves the axon helix of neuron C and see how it settles on the receiving postsynaptic neurons. So it moves from here, and if you follow it, it's going to land on the first buffer, the third AND gate, the first AND gate, and the second AND gate. Follow it again. It starts from C. If you follow it, it will end on the first buffer, the first AND gate, and the second AND gate. All right, so let's look at it. This is a buffer. The first buffer is a buffer. What we said about a buffer is that it receives input, and because it's a buffer, it will just relay the input that it received out. So once it receives excitation, it's just going to relay that excitation out. So we expect that the first buffer will relay out its excitation. Now, the first AND gate, which is an excitatory AND gate that we see here, remember it's an AND gate. It's a 3-input AND gate, which means you need all 3 inputs to fire, to bring in action potential, to open up channels within the neuron before that neuron will fire. So you need 3 inputs to be able to raise the membrane potential of this neuron to negative 55 millivolts before it can fire an action potential. The second AND gate, if you look carefully, you see that AND gate is an inhibitory neuron. It is a 2-input AND gate. So you need 2 inputs for this AND gate to fire. So clearly, looking at this, you can see that none of the 2 AND gates would fire. Only the buffer neuron will fire. So when we progress this, we see that none of those 2 AND gates will fire. Only the buffer will generate an action potential that will travel all the way down to the receiving Z neuron for processing. Now let's consider that Z neuron. The Z neuron is an OR neuron. So it's expressing OR logic, which means if any of the excitatory signal fires, Z will also generate an action potential. So since the buffer is bringing in, is sending out an excitation to the Z neuron, then the Z neuron will fire in this case. So it fires, and you see clearly that it obeys the rule of the second rule, where A is 0, B is 0, when C is 1, Z fires, like we see there. So it fires out, and then we have Z. So let's consider the third situation. In the third situation, A is 0, B is 1, and C is 0. So we have it here. A is not firing, B is firing, C is not firing. Again, if we follow this action potential and see where it terminates, where the axon terminal terminates, we find out that the action potential leaves A, nothing leaves A, sorry. The action potential leaves B, and nothing leaves C. And then at the end, we have it terminating in these respective neurons. So in the second buffer, you discover that the action potential comes in there. But because it's a buffer, it's going to just relay what has come in out. So it's going to also fire an action potential. Look at the action potential from B also. The axon terminal also gets to the first excitatory neuron, the AND neuron there. But because it's the only one, you need 3 of such excitation before that AND neuron will fire. So because it's only one, that AND neuron will not fire. And then the last one is the inhibitory AND neuron, the very last inhibitory AND neuron in this column of neurons. That is also a 2-input neuron. Now, because only one of them is firing, then that particular neuron too, this particular neuron we are looking at, will also not fire. So the only thing that will fire in this situation is this buffer. So the buffer will be the only one that will generate an action potential that will eventually get to the Z neuron that's expressing all logic. And because it is an excitation coming into the Z neuron, the Z neuron will fire its action potential, thereby obeying what we have in the third rule. All right. If we move to the fourth rule, where A is 0, B is 1, A is 0, B is 1, C is 1. What that means is A is not firing, B is firing, C is firing action potential. So if A is not firing action potential, B and C are firing action potential, then the axon terminal will eventually release neurotransmitters to the postsynaptic neurons. Let's see what those postsynaptic neurons will be. If you follow the axon and go to their terminal, you find out that the postsynaptic neurons are the ones that receive these neurotransmitters. So we say that the neuron, the first buffer, will receive that excitation, and because it's a buffer, it is going to relay whatever it receives. The second buffer also receives an excitation. Because it's a buffer, it also relays what it receives. The third one, the third neuron on that role is an AND, is a neuron expressing AND logic. But remember, it's a 3-input AND logic, so it needs 3 input before it fires. But here we see that only 2 inputs are getting to that neuron. So because only 2 inputs are getting to that neuron will not fire. We move to the inhibitory neurons. The first inhibitory neuron expresses AND logic. It's a 2-input AND logic. But because only 1 input is bringing in neurotransmitters here, that neuron will not fire. The last neuron there is also an inhibitory neuron expressing AND logic. Again, 2 inputs are required for it to generate an action potential. But because only one of them is being triggered, that neuron will not fire an action potential. Thereby, only the 2 buffers will fire action potential. And those action potentials will travel from those 2 buffers and they will hit the Z neuron. The Z neuron will sense that the 2 buffers are bringing in excitatory signals. And remember, it's a all or nothing. So whether it was only 1 buffer or 2 buffers, it's immaterial for the Z neuron. So it's going to sense these 2 inputs coming in. Then it's going to fire an output that will travel to do other things within other circuits. Okay, let's look at the 5th rule, where A is 1, B is 0, and C is 0. Again, these are conditions that we've seen before when B was 1 and C was 1, while others were 0. So the same thing you have here. The axon terminals, the action potentials will travel along the axon and get to the axon terminals, contacting those postsynaptic neurons. So only 3 postsynaptic neurons will be contacted, and these are the 3 AND gates. The first AND gate that is excitatory and the 2 inhibitory AND gates. Now, because those AND gates require, like the first AND gate requires 3 inputs for it to generate an action potential, but only 1 is coming in, so it will not fire. The second AND gate requires 2 inputs before it can fire, but only 1 input is coming in, so it will not fire. The third AND gate requires 2 inputs for it to fire, but only 1 input is coming in, so it will not fire. So at the end of the day, none of those neurons in those rules will fire action potential. Consequently, no action potential will travel from those neurons to the Z neuron expressing all logic. Consequently, the Z neuron will not fire anything. So nothing will happen in this circuit. And clearly we can see from the truth table that when A is 1, B is 0, and C is 0, then the output will be 0. Now let's consider the 6th situation. 6th situation. A and C are firing action potentials, but B is not firing. A fires, B doesn't fire, and C fires. So if you follow these action potentials to the axon terminal, you find out that they will terminate on these respective neurons shown here. They will terminate on the first buffer and on the 3 and expressing logic neurons. So the first neuron requires 3 inputs for it to fire. However, there are only 2 inputs coming into the first logic expressing AND gate, which is the 3rd neuron in this situation. So because only 2 inputs are coming in, this first AND logic will not be triggered. So this neuron will not fire any action potential. The first one is the buffer. We know clearly the buffer is going to fire an action potential because whatever it receives is what it will relay. So the buffer will fire an action potential, but the neuron, the first neuron expressing AND logic, will not fire. And let's consider the 2 inhibitory neurons. So the first inhibitory neuron, which expressing AND logic, you clearly see that 2 inputs get into that AND logic. Now, because 2 inputs are coming in, and it's a 2-input AND gate. So because 2 inputs are coming in, it is going to fire an action potential. The condition is satisfied, so it will fire an action potential. So the last one is also a 2-input AND gate, but because only 1 input is coming in, it will not fire an action potential. Consequently, what we are going to have is this. The buffer will fire an action potential, and the first inhibitory neuron will fire an action potential. These 2 action potentials will travel all the way to the Z neuron. When they get to the Z neuron is an OR expressing logic. But remember, the buffer brings in action potential. The first AND logic, the first inhibitory neuron also brings in an action potential. But the buffer is saying fire. The inhibitory neuron is saying don't fire. So you can imagine 1 fire, 1 says don't fire. So it's a voting. So if you sum that up, that will be 1 minus 1. 1 minus 1 is 0. So because the neuron Z does not receive the sum of what is coming in, is not telling that neuron to fire, the neuron will not fire. So 1 minus 1 will cancel out, and so the neuron will not fire. And so we can see from this logic table that when A is 1, B is 0, and C is 1, the neuron Z does not fire. So nothing happens on Z. Now let's look at the 7th row, where A and B are both firing, but C is not firing. That is A1, B1, C0. So if A and B fires and C does not fire, the axon terminals of A and B will end up on the following neurons. So we are going to find out that the second buffer will fire. It will fire because it receives input, and because it's just a buffer, it will relay that output out. The first neuron that is expressing AND logic, that is excitatory, is a 3-input AND logic, but only 2 are coming in. So that neuron will not fire. It requires 3 before it fires. The first inhibitory neuron requires 2 inputs. It's an AND logic. It requires 2 inputs to fire. Only 1 is coming in, so it will not fire. However, the last neuron is an AND logic requiring 2 inputs, and the 2 inputs are provided. Consequently, the neuron will fire. So what we have is that the buffer will fire and this last neuron will fire. Their action potentials will travel all the way on the axon and land on the Z neuron. When it gets to the Z neuron will see that one buffer is saying fire, another one is saying don't fire. And that's a situation like we had previously. 1 minus 1, and the answer is 0. So it's a voting. 1 says fire, 1 says don't fire. So they cancel out. Consequently, the Z neuron will not fire. And so if you look at our truth table, you see it's satisfied. When A is 1, B is 1, and C is 0, Z output is 0. It doesn't fire. Now, let's look at the last situation in this truth table, where A is saying fire, B is saying fire, and C is saying fire. Z is supposed to fire in that situation. Let's see if that happens. A is saying fire, B is saying fire, and C is saying fire, action potential. The axon terminals will terminate on all of those neurons, and then you are going to have this situation. All the neurons will receive input. So the first buffer receives input. Because it's a buffer, it will relay its input out. The second buffer receives input. Because it's a buffer, it will relay inputs out. Then the first AND gate is a 3-input AND gate. 1, 2, 3, and all 3 inputs coming. Consequently, that neuron will also fire. The first inhibitory neuron is also an AND gate. 2 input AND gates, and the 2 inputs are satisfied, so that neuron too will fire. The last neuron, also inhibitory, receives 2 inputs, and those 2 inputs are satisfied, so that neuron too will fire. So we'll have a situation where all 5 neurons will fire action potentials through to the Z neuron. So they will fire action potentials that will travel all the way to the Z neuron. So what happens at the Z neuron? The Z neuron is an OR logic, which means if it has any of them, any of the excitatory signal coming in without anything inhibiting it, then it will fire. So if you look at this clearly, 3 of them are saying fire. 2 of them are saying don't fire. So if you do the voting, that will be 3 minus 2. The answer is 1. So the net addition of the net effect of all these 5 neurons is a 1, telling the neuron to fire. So consequently, neuron Z will fire an action potential. That action potential will travel all the way from Z to any other circuit within the brain or somewhere in the nervous system, and it will do something. So this method of designing logic circuit, of minimizing number of neurons you need, was designed by Wale Odunsi, a member of the atencephalon family. It's a proprietary method that was designed by him and is working for all intent and purpose of our research. So we might also draw this circuit like this, because if you look at this first one I have, there are only 1, 2, 3, 4, 5 inputs coming into the Z neuron. You could as well have 6 inputs. There are some circuits we designed to be 6 inputs, 7 inputs, 8 inputs. So in order to minimize lines crowding around the Z axis, we designed the Z neuron like this. So the only thing that has happened is that we are saying that this straight line you have here is the dendrite that receives all the inputs, right? So it gives us the opportunity of adding 6, 7, 8, 9, 10 without necessarily crowding this Z neuron. And then the sum of all that is fed into the Z neuron, and that determines whether the Z neuron will fire or not. So this is just a representation of this. This and this are both the same. I have only drawn this here so that I can show you that rather than drawing several lines towards the Z neuron, we can minimize the number of neurons lines going directly to the Z neuron and just draw it on a line and feed the input of that line as the input from the dendrite down to the neuron. All right. We could also draw others. These other ones that we have, the AND logic that you see here, 3 inputs, 2 inputs, 1. It is easy to draw now because they are just 3 inputs, but we can have a very long circuit where like 10 inputs are feeding each logic. So it will be a 10 input AND logic. So when we have situations like that, it's better to just represent it just the same way we did with the Z, where all the 3 inputs feed into the dendrite, and the dendrite will now pass that information to the neuron, where the neuron will take a decision based on the inputs coming in. Same thing you have here. These 2 inputs and then this is 1 output. Thank you very much for listening, and we'll continue our discussion in further lectures.